What is the duration of your lecture, Anvedan? 1 hour or 1.5 hours?
45 minutes.
45.
Good afternoon, all. Good afternoon, Anirudhan ji.
Very good
Yeah,
afternoon.
good afternoon. Good afternoon.
Random day. This is a very interesting lecture series we are having. Hello, good afternoon, Nilima.
Good afternoon. Good afternoon. I'm sorry.
Good
Sir,
afternoon.
Anirudhan sir, good afternoon.
Good afternoon. Yeah. Thank you.
Good to see you. So Balakumar sir also joined. Arindam also
Yeah.
joined.
Meenu has
Yeah.
joined. Lot good presence.
Hi Arindam, how are you?
Yeah, all good. How are you doing?
All fine as usual. I just came from office because I rushed because there was then big highways going on, and because of that road construction, internet is highly unstable in office. So I just rushed to home for this.
Oh, okay, okay.
Today TC220 chair Andrew and secretary both are traveling, so they could not join. To send their apologies, but I think Dr. Anil is also not able to join because he's also traveling. So we have only Dr. AP here from
And
IG.
Nilima and speaker, our main speaker is here, so no need to.
I hosted sir when I was in IIIT Hyderabad long time back. You remember your talk on IS 2911? Anirudhan sir,
Yeah, yes.
I think sometime in 2013 or 14.
2012, 13 minutes.
And so just for information, this lecture will be recording and it will be uploaded as well. So we'll start. Sir, will that be okay? Shall we start?
Yeah, we can
Yes.
start.
Yeah, we can.
So good afternoon, everyone, and welcome to this TC220 lecture series as a part of TC220's field monitoring geomechanics. And we are doing this event as a curtain raiser for our conference also, which will be on field monitoring, 12th ISFMG conference on field monitoring, and that will be at Indore. So we bid this conference 2 years before, and we started the event conference website also. I hope like the details are all with IGS members. So I welcome all the members of IGS and ISMG members to this international lecture series. And this particular lecture is very interesting because we want to focus, because the speakers are from different parts of the world, and this is from our Indian case study. So it will be really interesting. And so I should thank our today's speaker, Dr. Anirudhan sir, to accepting this invitation and sharing his knowledge. So first of all, thank you so much. So with this brief information, I request our Honorary Secretary of IGS, Dr. AP Singh, to say a few words, and then we will start the lecture. Dr. AP.
Yeah. Good afternoon to all, and congratulations to Nilima for starting such a useful, very useful lecture series. And now we are having ninth lecture of this series, and all the lectures are delivered by very prominent speakers, experts of this field, and hopefully we are doing a very good preparation for the coming conference symposium at Indore, which will be in 2026. So I express my thanks and gratitude to even Aniruddhan sir for taking the pain and delivering the talk today, and wish a very grand success for the coming conference. So thank you very much, and let's start the.
So thanks, Dr. AP. And sir, it's my honor to introduce you to our participants today. So I'll just take this opportunity. So with a brief bio of yours. So Aniruddhan sir is a geotechnical consultant based in Chennai. And he graduated in civil engineering with specialization in geotechnical engineering from IIT Kanpur in 1981. After obtaining BSc Engineering honors in civil engineering from the University of Calicut in the year 1979. His career as an independent consultant started in 1987 after associating with a leading consultancy firm for 7 years. His major field of expertise is in deep foundations, ground improvement, and geotechnical characterization. So his organization, Geotechnical Solutions, executed more than 2,000 small and medium geotechnical investigations and provided foundation recommendations to several projects. So he is actively involved in the activities of Indian Geotechnical Society and Deep Foundations Institute of India, and conducted several conferences, workshops, and seminars. So he was the chairman of the Deep Foundation Institute of India. He also served as the chairman and honorary secretary of the Chennai chapter of the Indian Geotechnical Society. He is a member of TC 302 of ISMG on forensic engineering, TC 301 of ISMG on historical sites, as a convener of TC 04 of the Indian Geotechnical Society on investigations. So he has authored and published several technical papers, guidelines, manuals on lateritic soils, and his guideline manual on geotechnical investigation and the design manual for continuous high gut piles are also available. So with this very brief introduction, so sir, I thank you again for accepting our invitation to be part of this lecture series, and so request you to kindly start.
Yeah, thank you very much, Nilima. So I'll share my presentation. Let me see. Yeah, are you able to see the screen?
Yes, yes.
Yeah, thank you once again. Nilima, I'll be talking briefly on monitoring and performance, or for performance, based on a couple of case studies I have. And let me first play some acknowledgements to my to the TC 2020 team, my teachers, again Professor Nilima Satyam, and especially Professor Ilamparadi, Dr. Balkumar, and Mr. Madan Kumar, and my other professional friends. So without this, their help, I would not have reached to this level. So thanks to all my professional friends. The picture what you see on the screen is one of my paintings, one of my personal hobby, and which was not happening for so many years. I started doing it again last year. So this is one of the recent paintings I made on Bogibeel Bridge in Assam. And when we talk about monitoring, we ask why we do field monitoring, and what do we monitor, if at all we are doing any monitoring. And then I'll present a couple of case studies on performance or monitoring for performance study, and go with some concluding remarks. So why do we need to monitor a geotechnical structure or geotechnical activity? We all know that the soil is, or the ground is very complex, and understanding of its behavior is not very simple. However, we simplify the ground and substructure models to satisfy a design, and we often resort to finite element and finite difference analysis to solve more complex problems. We make several geotechnical assumptions for fulfilling this design. We assume certain stress strain models, a construction sequence, and all the geotechnical risks tackled by a concept of factor of safety. During the design process, we make predictions, especially about the foundation or ground movement under the design geotechnical activity. So all these assumptions and predictions are based on our experience and whatever literature we have. And many researchers have produced literatures based on their studies. So we use these references to make our assumptions and predictions, but we have to still validate these assumptions and predictions. We can see that the simplified methods may not often predict the behavior very accurately, and we need to make measurements to confirm our assumptions and predictions. So monitoring of geotechnical structure confirms the performance, and to some extent whether we were good in predicting or assuming, making certain assumptions and predicting the performance. And it is important to decide on what we monitor for achieving our goal for validating our design. Commonly monitored parameters are the movements in the ground and the structure. Those are predicted during the design analysis. We also measure excess pore water pressure when we deal with the improvement of soft clay deposits. And occasionally we measure the stresses and strains in the foundation elements in the soil also, like in the case of retaining walls or deep foundations. So what do we gain by this field monitoring? The monitoring helps the designer to make necessary changes in certain cases. We can also provide inbuilt warning stages for attempting mitigation measures if found necessary. Monitoring reduces the geotechnical risk. Most of the geotechnical risks are highlighted when we monitor structure, and we can take timely action to rescue the structure, or we can make amendments, or we can do additional precautions to make the structure stable. I'll present a couple of case studies in which I was involved in the design and execution, and also the performance monitoring. One of the cases large diameter ammonia tanks on short piles. This project was executed in 1983, just after my graduation, and this was my first assignment or field assignment after my graduation. The site is Paradip Phosphates factory in Orissa that was built in 1983. There were 13 large diameter steel tanks storing liquid ammonia, phosphoric acid, and sulfuric acid. Also, all these tanks imposed roughly 180 kilonewton per meter square pressure at the tank base. There were also two fuel oil tanks, which are all smaller size, built on ring wall foundation because the loading was about 100 kilonewton per meter square. And the project owners we decided to support it on ring wall with the minimum ground improvement of replacing the top 2 meter soil. The subsoil conditions in the site comprises loose deposits up to about 5 meters, followed by medium and dense soil layers, mostly sandy type soil. In the 80s, the small diameter driven cast institute piles were very common, and the maximum size of any pile foundation was 600 mm. That was in the case of board piles. So in this project also, they decided to go for driven cast in situ piles of 50 millimeter diameter, driven to a depth of 27-meter long depth. This was the proposal given by the main principal consultant, and we were appointed later by consultant for some structures in the site, and this ammonia tanks design of ammonia tank foundation came to our scope. So we found that there are a lot of challenges in constructing 27-meter long driven cast in situ piles. Those who are involved in driven or seen how the driven cast in situ piles are installed, we know there is a lot of difficulty in handling such long tubes. And even if you use followers, we find a lot of difficulty in handling such large follower tube. And the dropping of concrete from such height can also result segregation of the concrete. Usually, the allowed dropping height in the case of driven cast in situ piles is something like 18 to 20 meters. And there is also difficulty in handling very long reinforcement cages. And of course, the long piles, because of all these issues and additional requirements, it cost very high compared to normal standard length of driven cast in situ piles. So we have to look for alternatives to tackle all these issues. And because of the large loading, because the tank is of 18-meter height, we had to go for the foundation, and the shallow foundation was not adequate. So we have to make a lot of analysis for alternative, like different length of piles. For finalizing the design. We all know that a single pile has very small settlement. We usually measure 6 to 10 millimeter settlement for individual piles when it is loaded individually. But when the piles are installed in a large group, it results very large settlement because of the very large influence zone involved under the large group. Not like for a single pile, we have a very small influence zone, and in the case of very large group, we have a very large influence zone, resulting very large settlements. So we had to do detailed settlement analysis for different options. During 80s, we had very limited procedures available for estimating the settlement of large group of piles. And one of the most accepted procedure was assuming equivalent draft at some depth, usually at 2/3 pile length, because of the friction developed along the pile, and we assume that the load is transferred to 2/3 of the pile length. Then it acts like a full draft foundation. Then it distributes from that point, like a normal flexible raft foundations. We used Boston's stress distribution below the ground for estimating stress levels in different layers, because the profile comprised of several layers. We estimated the compression of sand layers using the DBIR procedural expressions. These are the standard procedures we used to adopt in those days. And after having the estimation, we analyzed a foundation without pile, which resulted very large settlements, something like 200 to 300 millimeters at the center. And we analyzed the settlement of a long pile foundation, which resulted about 40 to 60 millimeter at the center and 33 to 45 millimeter at the edges along the periphery. Because of the piles, we have a pile soil interaction, increasing the settlement along the periphery little more, and marginally reducing the settlement at the center. So we expected about 40 to 54 millimeters along the periphery in the case of 27-meter long pile foundations. In the case of shorter piles, like 10-meter and 14-meter, because we decided not to go for 27-meter long piles because of the construction issues, we used a construct and usually being done in those periods. So we tried analyzed 10-meter pile and 14-meter pile cases, and we found these settlements are not varying so much, and it was in the range of 60 to 100 mm at the center and 48 to 64 millimeter in the periphery. So because of the pile soil interaction, we expect little more settlement along the periphery, while we expect a small reduction at the center. So we went for shorter piles below the ammonia tanks and acid tanks. We provided 437 piles of 10-meter long and with individual pile capacity 55 tons. So the 10-meter pile, we expected a settlement in the range of, the maximum settlement we expected was 107 millimeter at the center and 64 millimeter along the periphery. But because of the interaction, we expected about 85 millimeter along the periphery once we do the full loading of the tank. So we first monitored the performance of the individual piles by way of conducting individual pile load test, and we found the maximum settlement under 62.5 kilonewton load. It's about 5 mm and with the average elastic rebound of 28 millimeters. So this is a usual finding for any piles that is having friction as well as end bearing, and the individual piles were performing as we expected. And we decided to monitor the tanks during hydro test with 8 observation points along the periphery and 1 at the center. And we installed one individual single pile as a reference point approximately 50 meters away from the tanks to use as a reference for measuring the settlements. So we used a very simple method of water tube level measurements for measuring the settlement along the boundary as well as at the center. In this case, the measurement at the center was not difficult because the tank foundation had 2 slabs, one at the ground level and one at about 1.8 meter above the ground. So we were able to go underneath the tank to make any measurements. We loaded the tank in 4 stages, 6-meter water fill, which was maintained for about 1.5 months. Then we filled up to 10 meters and waited for 2 months, and 14-meter with 2.5 months holding period, and the maximum water load of 17.9 with the 3 months holding period. So the observed settlements are presented here. You can see these firm lines are at the center and these dotted lines are at the periphery. So we measured maximum settlement at the center as 65 millimeter in one tank and 105 millimeters in the another tank. And along the periphery, we observed 50 millimeters and 78 millimeters. Whereas the estimated settlements were 78 to 107 millimeter at the center and 63 to 85 millimeter along the periphery. This is a plot between the edges and the center. This is at the center of the tank, and this settlement is at the periphery. This firm line represents the estimated value, and the dashed line is the observed settlement during the hydro test under the maximum load. You can see a considerable comparison between these two between observed and estimated settlements, except in the case of one tank, we had a much smaller settlement than what we estimated. And we also observed a typical saucer shape settlement profile similar to flexible draft when the group of pile with the common draft was loaded. We also had the opportunity to hydro test fuel oil tank, which is on ring wall and compacted soil fill. Because these tanks were only 10 meters, we made a comparison between the settlement we observed during 10-meter water height in the case of acid tanks. We can see that the large tanks on pile foundation settled some 20 to 40 millimeters at the center, whereas the smaller tank with on shallow foundation settled more than 150 millimeters at the center. And this tank also experienced a minor tilt because of the variation in the soil profile below the ring wall. In this case, we could measure the settlement at the center of the tank using a buried triple tube settlement marker that was fabricated by us during those days. It was a very simple measuring unit which can be used at any point below the tank, buried under the tank, in the soil below. And the summary of performance of tanks on pile foundations, you can see that the influence zone of the single pile is very small, resulting very small settlement, while the large groups settles much larger, sometimes 12 to 15 times larger than the single pile settlement, of course, depending upon the soil profile below. And we have standard procedures available for making these estimations. So we have seen that the standard procedure of equivalent raft procedure is reasonably good enough to make a reasonable assessment of the settlement of the large tanks supported on pile foundations. And we have also seen that even though the piles are shorter, we could reduce the settlement significantly in the case of such heavy tanks of large diameter compared to those tanks supported on shallow foundation. Now, I also take pride in participating in the design of one of the largest gypsum pond in the country. This is also in the same plant, and I can say that this is one of the best developed gypsum pond in the country. So this is the recent Google photo of that gypsum pond. Coming to the second case study, this is about a commercial project in Chennai that was constructed in 2016 in a semi-urban environment. So there are a lot of constructions, existing buildings. When we had to make this construction with the 3 basements, we needed 12-meter deep excavation, and the available setbacks up to the boundaries were very limited. And the owners decided to go for 600 millimeter thick diaphragm wall as a retention system for this deep excavation. There were 2 levels anchors also along with the diaphragm wall. So this was the retention system used in this project. We had this diaphragm wall going up to very dense sand stratum at this point, and the 2 anchors also extending into the dense sand stratum. So we had clay layers up to about 18 meters, and we could not provide any anchor before this level because the anchors were extended only to the clay layer without producing any required capacity. So we have to start the first anchor at 6 meters, which was a calculated risk at that time because usually we allow a cantilever length of 4 to 4.5 meters for open excavation with diaphragm walls. So the diaphragm wall extended into very dense sand and sometime into weathered rock also, depending upon the profile available at the location of the diaphragm wall. The excavation was to be done in 3 stages. That was, first stage was at 6.5 meter, after which we installed the anchors at 6 meters. Then the next stage of investigation, the excavation was 10.2 meter. And the anchors were installed at 9.7 meter. Then the last final lap of excavation was up to 12.5 meter. We also made instrumentation and monitoring arrangement for instrumentation and monitoring using inclinometers within the diaphragm wall. These inclinometers were installed for the full length of the diaphragm wall. And the wall movement was monitored almost on daily basis as the excavation progressed. And we also had visual examination of the ground during the excavation. So I will present a case the experienced during the excavation up to 6.5 meter only in this presentation, because that was critical for us, and which gave a lot of surprise to us, or maybe a lot of concern during the execution. So what we expect of a behavior of a diaphragm wall like this when we excavate without any lateral support, like any strut or any anchor. So we expect a very true cantilever performance, like the wall will be bending like this and the ground settles like this. And when the wall is bending like this, we generate a bending moment in the wall towards the soil side. The tension will be on the soil side. This is what we expect during excavation without any lateral support for the wall. So we did the detailed analysis initially using WALAP program and later using Plaxis 2D. In the case of Plaxis 2D, we used more Coulomb and hardening soil model for the clay soil up to 8 meters. But we used untrained B-type soil for inputting the parameters. In the case of untrained B, we input untrained cohesion as the shear strength and all the stiffness parameters as effective strength parameters. So the effective modulus and effective Poisson's ratio. And we also apply an interaction in interface factor of 0.7 between the soil and the wall, assuming that the soil is in contact with the wall all along. So the analysis were carried out using these parameters and with the 0.7 meter interface friction. But surprising to us, the actual wall behavior was showing something like this instead of a true cantilever after the analysis. And this blue line was resulted by the WALAP analysis, which is a limit state equilibrium procedure. And with finite element, we had this sort of shape after the first 6 meter excavation, which is not a true cantilever behavior. So there was some concerns why the behavior is like this. And the bending moment distribution also showed totally opposite to what we expect. We had the bending moment developed on the other side of the wall, whereas we expected a bending moment developing on this side where the tension will be on this side, but the analysis showed the tension on the other side. We could not resolve this reversal of bending and deflection even after using the hardening soil model suggested by some researchers. This was a design challenge that was not resolved during the design stage. when we went for the actual excavation, we started observing the diaphragm wall movement during excavation. When we reached 6.5 meter excavation on the basement area, we found a gap between the wall and the soil, a clear gap between the wall and the soil. This depth of the gap went up to 3 to 3.5 meters. So we can put a rod, small diameter rod through this to depth of 3 to 3.5 meters. So there was a clear gap between the soil and the diaphragm wall. And the measured deflection through the dinclometer was like a cantilever wall as we expected. So this is the measured deflection of the diaphragm wall through kilometers. If you remember, we expected or we estimated a deflection like this, whereas the actual observed deflection was pure to like a pure cantilever wall. So this was what we are expecting, but the predicted deflection was from the analysis was like this. Then, unfortunately, for the project, there was an unexpected rains, and the anchors at 6.6 meter could not be installed, and the work was stopped. But the measurement of the wall movement was continued, and we observed very large deflection after the rains, which went up to 60 millimeters. Whereas in the initial stage, it was only 30 millimeters, which increased to 60, 70 millimeters after the rains. So there was a sudden increase in the settlement, obviously because of the very increasing groundwater table and the increased weight of the soil because of the saturation. Then there was no change for about 22 days, but all of a sudden the gap between the wall and the soil got closed, and the wall suddenly moved to 100 millimeters. So if you look at the estimated deflection of about 30 to 40 millimeters, what we observed was about 90 millimeters, which was of very high concern for any designer and executor. So if we summarize the monitoring after 6.5 meter excavation, initially during the dry spell, it was deflecting like this. And after the rain and when the soil got saturated and with high water table, it moved to 70 millimeters. Then all of a sudden it moved to 100 millimeters, and the gap between the wall and the soil closed. So this is the summary of the monitoring of this tank during the first stage of the excavation. And as I said, the estimated deflection was very small and in a different shape as such. So there was a significant concern about the performance of the wall, and we had to do a review of the design, especially because the diaphragm wall behavior was totally different from the design, and wall deflection is 2.5 to 3 times larger than the estimated one, and failure conditions can be different. And the stability after final excavation of 12.5 meter is also of a big concern, because when it moved already 100 millimeters, what would happen to the wall when we excavate up to 12.5 meter? And the main indicators of the monitoring was there was a gap between the wall after the excavation, that is during dry stage. Then the soil got saturated during rain and water table raised, and it moved again. Then all of a sudden the wall, the gap between the wall and the soil closed, and allowing the wall to move further. So the gap closure of the wall and the wall movement indicated more load on the wall. So we had to do a review of the analysis, and we did in 3-4 stages. The first stage was we analyzed the wall again with zero interaction, because the gap between the wall and the soil indicated that there is no interaction between the wall and the soil during the first stage of excavation during dry condition. So we assumed a zero interaction between the soil and the wall to do the first stage investigation, the analysis. Then we saturated the soil behind the wall and raised the groundwater to the about 0.5 meter below the ground and analyzed again. So these dashed lines are the estimated values, and the firm lines are the measured deflections. So here we can see there is a good comparison between the estimated one and the revised estimated one and the actual measured deflection. So we understood that we are in the right path of reviewing the design. Then we have to see the last, the final stage of the wall movement, in which the gap was closed. We assumed that the soil has moved as a block, but that was not happening in the Plaxis analysis automatically. So we have to induce some block failure mechanically in the model. And we analyzed and got deflection of the wall. This dashed line is the deflection estimated from the analysis, whereas the firm lines are the actual deflections. We also estimated very high bending moment. Fortunately, it was marginally less than the maximum bending moment we got after the final excavation in the initial analysis. And because of the unexpected behavior of the wall during the first excavation, we decided to go for very high design bending moment, even though we got a smaller bending moment. So that saved the structure from any failure because of these large deflections. So we also had to do the analysis for the next two level excavations, that is up to 10.2 meter and 12.5 meter. And with two anchors at two levels. So we did that analysis, and we got the deflection, expected deflection like this. And this is at 10.2 meter excavation. This is at 12.5 meter excavations. So after the full excavation, we got the measurements from the inclometer, which is really matching with the expected performance of the wall. After the revised analysis. So some of the concluding remarks based on this case studies. The monitoring of foundation behavior has a great importance. Monitoring helps to confirm the design and analysis. And monitoring brings out anomalies in the assumptions, provides insight for better and realistic analysis, and facilitate adequate revision in the design and mitigation. If you have any questions, this is my presentations. Thank you. I think I took 40 minutes.
Can I
40
ask
minutes.
something? I'm Dr. Dhawan from Delhi.
Yeah.
Can I ask something?
Yeah,
Very
please.
good, very good presentation, but based on my field experience, this you did the monitoring part. What type of sensors did you use, and what was the location?
No, we used only in kilometers. The tube is installed with the guide walls, the guides in the tube, and we lower the inclometer and measure the inclination of the tube. It's only simple measurements. That is for the wall. And for other tanks, we used only water tube measurements. Nothing sophisticated we used in this monitoring.
See, your excavation was 12.5 meters. So you
Yes.
said first layer 6.5,
Yes.
then 6.5 to 10.5, I mean, what are the extra things that you have to take care of the excavation for the excavation?
Yeah, as I said, the 6.5 meter excavation was a calculated risk for us because we decided to have only 4 meter excavation without any anchors. That was only safe for 600 thick wall. But because of the soft layers up to about 16, 17 meters, we could not put the anchors in a proper soil because of the limited setback and the rock level was deeper. So we had to put our first anchor at 6 meters. That was one of the mistake I would say that we did in this design. We should not have allowed more than 4 meter excavation without any lateral support.
I see. So you
because-
first went for 4 meters, then 6.5, then further you went down to 12.5.
Yeah, but 4 meter we could not do it because there was no good soil to put our anchors at that level. Even if we put a very 60-degree also, it will not be working so effectively. So we have to go to 6.6 meter to have a proper anchoring at that point. We also could not put the studs because the process that excavation stages was localized, not the entire area we could excavate at same level. So we could not think about studding also at any point.
Then my final one, the geotechnical designs.
Yes.
You said you may go for route, then alternatively you went for pile foundations. I mean, how could you see? I mean, decide that whether you will go for route foundation or pile foundation?
You are talking in the case of tanks?
In the case of tanks, right?
The tanks
Good.
we went only for pile because it was heavily loaded and the soil was poor up to 5 meters. So if we had put normal ring wall and with some improvement, some soil replacement, it was giving a settlement of 300 to 350 millimeters. The structural engineer was not able to accommodate that much settlement for the steel, the concrete base at the for the ammonia tanks. So we have to go for
sorry.
we have
What
to
data
go
did
for
you give?
piles only. Yeah.
What data did you give as geotechnical expert to the structural engineer?
We gave the differential settlement between the center and the periphery, maximum and the minimum limits, and at different points, so that he can design the pile cap connecting all these piles. Only the smaller diameter pile helped us reducing the space between the piles because so many numbers we put. The space was something like 1.8 to 1.9 meters between the piles. So the structural engineer was able to design the connecting slab without any difficulty because it was designed as a highly flexural member.
Now finally structure is constructed in this shape.
Yeah, I'm Yalampurdi. Can I?
Yeah, please.
I'm Sandrutan. It's a wonderful presentation.
Thank you.
Very good detail you presented. I have one or two clarifications I need from you.
Yeah.
The first case, in case of the tanks, have you monitored load share in the central and jet files? Was there any sort of arching and relaxation was there? If it is monitored, we may be able to understand. That's what whether any.
No, we are not monitored in any stress level in the pile.
Okay.
But we could find that there is the interaction resulted in reducing the settlement at the center marginally and increasing the settlement along the periphery.
So it is trying to transfer from center to.
Yes. So the differential was reduced because of the pile foundations.
That's one thing.
Yeah.
Second question is on the deep excavation problem. The similar problem we also already discussed and we faced, particularly when we are having the top clay layer.
Yeah.
The deflection surface is not, shape is not matching
Yeah.
with what normally it has to be.
Yeah.
My one observation is, can we totally the factor 0.75, whatever you are given,
Yeah.
we can make it as a 0.
Yeah, that's what we did in the revised analysis. We made to 0 up to 3.5 to 4
Yeah,
meters.
that's what that could have been relieved, because and then again the problem more will be worse than that of the hardening soil model. Hardening soil model will get a much better representation than that of Mukuru model. Thank you to them. That's all my.
Yeah, thank you. Yeah.
Sir, we have some questions in the chat box.
Yeah,
So
one
can
second.
you please take?
Shall I close the presentation then?
Yeah, please. Maybe I think Parchani sir. So Parchani sir is a chief engineer here at RRCAT in Indore. So you can unmute also, sir.
Yeah, sorry. Yeah, I'm doing.
Hello?
Hello? I think we cannot hear you, sir. Parchani sir, are you there? I think some issue with the mic or something. Sir, I think you can take his question.
One second, I am not able to see the box.
So it's in the chat box. In place of diaphragm wall of 600 mm thickness, so will box type wall would be better, as it will be significantly enhance the lateral stiffness.
Yeah, it is possible, but the cost is also an issue. Because the 600 mm thickness, we initially thought of going for 800 millimeter thickness, but the cost was prohibitive for the client. So we had to go for cheaper solutions most of the time with the clients.
Yeah, okay. So there is another question from Prathamesh. Prathamesh, you are there, so you can unmute and ask yourself.
Good afternoon, sir.
Yeah, please.
Sir, as initially you modeled the diaphragm wall, but the actual results were not as per the modeling. But later you model again, and the actual results and the model results were similar. So, what were the major difference between two models?
Yeah, in the case of first modeling, we used both the time we used undrained B-type soil. But in the initial modeling, we used interface friction of
92.
0.7 interface factor. And because of the
silver space to base station.
Because of the gap between the wall and the soil, we understood that there is no interaction between the soil and the wall for the top 3 to 3.5 meters. So in the revised analysis, we used 0 interface factor. Instead of 0.7, we use 0.01 because the Plaxis do not allow 0.0 interaction. So 0.01 we used. And that was the first stage for the dry condition. Then for the rain condition, we used revised the parameters, like we used the saturated weight for the top soil, and we raised the groundwater table to 0.5 meter as we observed during the rains. But the initial design was with water level at 2 meter below the ground. Then we introduced a block failure in the topsoil, which is not automatically possible in the Plaxis, but we have to introduce a block failure, for which we provided an interface element, 45-degree interface element, in which we used a zero shear strength. So these are the changes we made in the reviewed analysis, revised analysis.
Okay, thank you, sir.
Thank you. Professor Nilima, I am not able to see the box. Somehow, I don't
Okay,
know
no
how
worries.
to-
I can read for you, sir. Otherwise,
Yeah.
yeah. So there is one more question from Saurabh. Saurabh, if you are there, you can unmute and ask yourself.
Yeah, hello sir, good afternoon.
Good afternoon.
Sir, actually I want to know that if I are going for the design of the foundation, whenever for the tank, so it is possible to load bearing any sharing of the raft foundation also and pile also.
Yeah,
Or not?
if we have a pile, we have to have a raft connecting all the piles,
Yes, sir.
or we have to use as a rigid inclusion without connecting the raft to the pile. So these two options are available. It will be like independent substructure
Thank you.
below. Yeah, that is possible.
हाँ
Yeah.
ना? तुम देखो डालना है, डाल दो, मुझे कोई प्रॉब्लम नहीं.
So, sir, any chances to sharing what percentage will be shared to the pile and raft?
Yeah, that we have to do a trial and error basis for the design, but otherwise we have to go for any three-dimensional finite element program to
Okay.
understand the sharing between the soil and the pile. We
Okay.
have also done some analysis with the Plaxis 2D with the help of Dr. Balakumar, but it has limitations when we use the Plaxis 2D for such analysis.
Okay. Now we can consider only for the pile, sir.
Yeah, for the pile, we can use pile, estimate the settlement, and for that corresponding settlement, what sort of load will be shared to the soil, because soil has a certain stiffness. Of
Yes,
course,
sir.
it will be slightly modified because of the presence of the pile, but still you can estimate what sort of load is transferred onto the soil. So you can always estimate what load is shared by the pile and soil in such cases.
Okay, okay. Thank you, sir.
Yeah.
So there is one more question from Mr. Vivek. Vivek,
Yes.
are you there? The question is, I have a question regarding block failure in soil. Mostly the blocks form in rock.
Excuse me, sir, I'm a geologist. I just wanted to know that in case of failure in soil, we take the angle, that angle is actually the angle of repose of the soil, or what? How we decide the angle, how the blocks will be formed?
It is like we estimate the angle of block failures 45 minus 5/2 when we measure with the vertical. So that will be the angle of the block failure. If it is clay, that 5 becomes 0, it becomes 45 degrees. It is very simplified procedure.
So with the type of material, the angle will change.
Yes, yes. If we have more friction, angle will be steeper compared with respect to the vertical.
Okay, sir. Thank you, sir.
Yeah, the participants, if you have any other question, kindly unmute and you can ask yourself. Okay, so I assume that there were no questions from others. Sir, with this, I sincerely thank you for sharing your experience with excavation monitoring. And I thank you again.
Yeah, thank you.
So thank you
Thank
so
you,
much.
Nilima, for giving this opportunity.
No, I was glad to hear to your practical experience. I know you have very rich experience, so I'm very happy to hear you again. So thank you so much, sir.
Thank you.
This will be recorded and we'll be updating this in the our IGS YouTube channel and also TC220 SMG YouTube channel. So I think all IGS members, I suggest you to follow that because a lot of lectures which are we are recording in the last 1 year we have been uploading there. So it's a good thing, like we should make our digital library as well. So with this, I'll say thanks again to all the participants for your time in participating in this lecture series. So see you in the next 10th lecture. Thank you so much. So thanks again.
Thank you.
Thank you, ma'am.
Thank you, Anuruddhan. Thank you, Professor Nilima.
Thank you.
Thank you, sir. Sanjay, sir, we didn't hear from you. Are you there?
Yeah, good evening. Well, as I just mentioned, it is very, very helpful. The explanation and the presentation was very nice, as always expected from my very dear friend Anirudh. So that's all I would say. It is something for everyone to learn that these are certain things which are very critical and important as a geotechnical engineer. That's it. Thank you.
Thank you, Sanjay.
Welcome.
So thank you so much. So we'll close this session. So thanks everyone. Good day.
Yeah. Thank you. Good.